Everyone, welcome to the channel. In this video, we shall try to learn about enzyme kinetics. And here in this heading, we have the theme kinetics. And in the field of physical chemistry, we know the meaning of kinetics as it is simply a branch that mainly deals with rate of reaction as well the factors affecting the rate of reaction. So kinetics will give a complete information about rate of the chemical reaction as well as the factors affecting the rate of that particular reaction. And here we are joining the term kinetics to the word enzyme. So hold on, solely we have enzyme kinetics. That means here in enzyme kinetics we used to learn about the rate of a reaction which is catalyzed by an enzyme as well the factors affecting the rate of that enzyme catalyzed reaction. So like how the rate of a normal chemical reaction will be influenced by various factors, the rate of an enzyme catalyzed reaction also influenced by some factors. And in this video we shall try to learn about the factors that affect the rate of an enzyme catalyzed reaction, and by learning the influence of those factors on the rate of an enzyme catalyzed reaction, what information we can brought up. So all those things we shall learn in this video. And first we shall see which are the factors that mainly affects the rate of an enzyme catalyzed reaction. So the first factor that affects the rate of an enzyme catalyzed reaction is temperature, and the second factor is pH. The third factor is the concentration of enzyme. So enzyme concentration also plays a very important role in understanding the rate of an enzyme catalyzed reaction. And fourthly, the concentration of substrate. So substrate concentration is very important in influencing the rate of an enzyme catalyzed reaction. And now we shall learn the effect of each and every factor that affects the rate of an enzyme catalyzed reaction. The first factor that influences the rate of enzyme catalyzed reaction is temperature. We know that if for a normal chemical reaction, when the temperature of the reaction system is increased, the reactant molecules will receive more energy, and that causes increase in the kinetic energy of the reactant molecules. And because of increase in the kinetic energy, there occurs increase in number of effective collisions between the reactant molecules. And because of increase in the effective collision, for a normal chemical reaction, the rate of that reaction also increases. And we used to say in general, for a normal chemical reaction, for every 10-degree rise in the temperature, the rate of reaction will get doubles. And that we already said in lower classes as temperature coefficient. That is, for every 10-degree rise in temperature, the rate of a chemical reaction will get doubles. That we already said as temperature coefficient. Like a normal chemical reaction, the rate of enzyme catalyzed reaction also influenced by temperature. But the difference between the normal chemical reaction and an enzyme catalyzed reaction is, in case of normal chemical reaction, with increase in temperature, the rate of reaction will go on increasing. But that cannot happen in case of an enzyme catalyzed reaction. That means the rate of an enzyme catalyzed reaction will increase with rise in temperature, but not continuously. It will be only up to certain temperature, but not beyond to that temperature. That means up to a certain temperature, with increase in temperature, the rate of enzyme catalyzed reaction also increases. But beyond that particular temperature, there will be no change in the rate of enzyme catalyzed reaction. The reason for that thing is when the temperature goes beyond to certain temperature with respect to a particular enzyme, above to the temperature, we know that the enzyme is mainly consisting of the protein part, that what we call as apoenzyme. That protein part above to that particular temperature, if you go on increasing the temperature, when it goes beyond to certain temperature, the protein part present in the enzyme, strictly speaking, the tertiary structure of that protein, the tertiary structure of the protein which is present in the enzyme will get destructed. That means will get destroyed. And when the tertiary structure of the protein got destructed, we used to say that protein got denatured. So when the protein part of the enzyme got denatured, obviously the enzyme will lose its enzyme activity. So because of this reason, when the temperature goes beyond to a particular temperature, the enzyme will lose its enzyme activity because of denaturation of the protein on account of destruction in the tertiary structure of the apoenzyme part of the enzyme. Therefore, the rate will increase for an enzyme catalyzed reaction only up to certain temperature, but not beyond to that particular temperature. And in general, with go on increasing the temperature, the rate of the enzyme catalyzed reaction will increase. But when the temperature goes near to the peak temperature of that particular enzyme, say in general roughly around 70 to 80 degrees Celsius. So up to this particular temperature, the enzyme activity will increases. That means with increase in temperature from room temperature up to this level. But when the temperature goes beyond to this temperature, the enzyme activity will get completely ceases. The whole and sole enzyme activity will get ceased because of denaturation of the protein. And when the temperature goes beyond to this, the whole and sole catalytic activity of the enzyme will be get lost. But once the protein got denatured, it lose its enzyme activity. That means when the protein part of the enzyme got denatured, the enzyme will lose its catalytic activity. But even though if you bring down the temperature, the enzyme will not show its catalytic activity since the protein part is already got denatured. That means once the protein part of the enzyme got denatured at relatively high temperature beyond to a particular temperature, even though you are bringing down the temperature, then also the material or the molecule won't show enzyme activity. The reason the protein part or the tertiary structure of the protein part of the apoenzyme will or got denatured. And you might get a doubt. So if you increase the temperature, if it goes beyond to a particular temperature, the protein part will get denatured and it will lose its enzyme activity. But if you decrease the temperature, what will happen? That also very important. So if you bring down the temperature from room temperature, so majority of the enzymes will work at normal normal body temperature, say at 37 degrees Celsius. So this is the normal temperature for a enzyme molecule. So this is the normal temperature at which the enzyme activity, majority of enzymes do show great catalytic activity. If the temperature goes very low, so say at 0 degrees Celsius, if temperature goes to 0 degrees Celsius, the enzyme, the whole and sole part, both coenzyme part as well as the apoenzyme part of the enzyme will get frozen. And at the frozen state, the enzyme will not show any catalytic activity. That means at 0 degrees Celsius, enzyme will get frozen, and at that particular temperature, there will be no catalytic activity by the enzyme. But one question may arise to your mind. So when the temperature goes beyond to a high temperature, the protein part will get denatured and the enzyme will lose its catalytic activity. But when 0 degree Celsius is reached, the enzyme will get frozen, and at that particular temperature there will be no catalytic activity. But at this temperature, the biomolecules, the protein part got frozen but not denatured. Therefore, still it can withstand its catalytic activity once it comes to the normal room temperature. That means, though the enzyme got frozen at 0 degrees Celsius, at 0 degrees Celsius it won't show any catalytic activity. But when it brought to the normal room temperature, again it start to show its catalytic activity. That means the loss of catalytic activity, or from the stage of no catalytic activity, the enzyme can be brought back to its active state. Okay, and we call that as inverse of inactivation. That means when you bring the enzyme from 0 degrees Celsius to normal room temperature, the catalytic activity of the enzyme will get regained. And therefore, we can say an enzyme can be stored in the frozen state for years together. And there will be no loss of the catalytic activity when the enzyme is in 0 degrees Celsius, because when it brought once again to normal room temperature, the protein part will comes to normal stage and again it will start to show catalytic activity. That's why at frozen state, say at 0 degrees Celsius, enzyme can be stored for years together. And as I said, majority of the enzymes will show the greater catalytic activity at the normal body temperature at 37 degrees Celsius. That is, majority of animal enzymes will show greater catalytic activity at 37 degrees Celsius. And some of the plant enzymes do show catalytic activity at relatively high temperature also. Say for example, the plant enzyme urease, which is used for the hydrolysis of urea. Urease do work as catalyst and do show its catalytic activity even at 60 degrees Celsius. And that is about how the temperature will influences the rate of a enzyme catalyzed reaction. And that influence can be explained in a graphical trend by taking the temperature along x-axis and the rate of the reaction in y-axis. So here you can observe the curve will appear like this. So here you can see, with increase in the temperature, the rate of the reaction also increases and reaches a very high maximum rate. The rate of reaction will be maximum at one particular temperature. But when the temperature goes beyond to that, again the rate will get decreases and almost reaches to zero, because there will be no enzyme activity, there will be no catalytic activity at all by the enzyme when the temperature goes beyond to that temperature. So only at a particular temperature the enzyme will show maximum catalytic activity. Maximum catalytic activity at this particular temperature. This is the general graphical presentation to express how the temperature will influence the rate of a enzyme catalyzed reaction. The second factor that influences the rate of an enzyme catalyzed reaction is pH. And we know that the pH of a solution will decide whether a given solution is acidic or basic. If the pH of a solution is between 0 to 7, that is acidic in nature, and if it is between 7 to 14, that is basic in nature, and if it is exactly 7, then the solution is neutral. Some enzymes will show best catalytic activity or maximum catalytic activity in acidic medium, and some enzymes will do show best catalytic activity in the basic medium. That means for each and every enzyme there will be a particular pH at which they show the best catalytic activity, and the pH at which an enzyme show maximum catalytic activity. The pH at which an enzyme show maximum catalytic activity. That pH is simply called as optimum pH of the enzyme, and at that particular pH, at the optimum pH, the enzyme will show greater catalytic activity. Say for example, the enzyme, say pepsin. Pepsin is having an optimum pH value of 2.0. That means pepsin will show greater catalytic activity in acidic medium. And on the other way, the other enzyme, that is trypsin, is having the optimum pH value ranging between 8.0 to 9.0. That means trypsin will show maximum catalytic activity in a basic medium. Like this, each and every enzyme will have its own optimum pH value, and by looking over to these pH values, you can say pepsin will be able to attack the substrate molecule best when the substrate molecule will carry positive charge. That means in acidic medium. So trypsin will be the best one, and it show greater catalytic activity since it attacks the substrate molecule when they are carrying the negative charge. That means the medium is supposed to be basic. Like this, in order to maintain a proper ionic strength by the substrate molecule, the pH is supposed to be maintained, and at that particular pH, the corresponding enzyme will show greater catalytic activity. That means they readily attacks the substrate molecule and forms the enzyme substrate complex, and that readily decomposes to give the product. So in this way, each and every enzyme will show a good or maximum catalytic activity at its optimum pH. But the problem is, if the pH value for a particular enzyme, if the pH value for a particular enzyme goes or will be made to drastic changes, if there is any drastic change in the pH value, then that causes the loss in catalytic activity or decrease in catalytic activity of that particular enzyme. So they should or they will show maximum catalytic activity on that particular optimum pH values only. If it is goes lower that particular pH or goes higher that pH optimum pH, then we cannot expect the maximum catalytic activity by that particular enzyme. So pH is very important for observing maximum catalytic activity by the enzyme. And here also we shall observe the effect of pH on the rate of catalytic activity by an enzyme. So pH. So as we said, the P with increase the pH, each and every enzyme will show greater catalytic activity. Each and every enzyme will show greater catalytic activity. That means they influence the rate of reaction. Only at certain pH, only at certain pH, the enzyme molecules will show greater catalytic activity, and thus it gives a maximum rate for that particular reaction. And below to that pH and above to that pH, the rate of reaction will be less. And that's about the effect of pH on the rate of an enzyme catalyzed reaction. The third factor that influences the rate of enzyme catalyzed reaction is the concentration of the enzyme. In order to understand what is the effect of concentration of the enzyme on the rate of reaction, when the remaining factors such as the pH of the solution, temperature, as well the concentration of substrate, when all these factors are kept constant, when these three factors kept constant, with increase in the concentration of the enzyme, the initial rate of the enzyme catalyzed reaction also increases. So you please notice the sentence what I am using. So by keeping pH, temperature and concentration of the substrate constant, the concentration of the enzyme, that is enzyme concentration, is directly proportional to initial rate of enzyme catalyzed reaction. Initial rate of enzyme catalyzed reaction. That means with increase in the concentration of the enzyme, only the initial rate of the enzyme catalyzed reaction will increases. That means with increase in the concentration of enzyme, the initial rate will increase. But as the reaction proceeds, means during the course of the reaction, as time proceeds, the concentration of the product will increases. And when the concentration of product increases, then the product molecule will start accumulating on the enzyme materials, because the amount of product will increases. As well, when the product formation increases, then the reaction will show a tendency to take back the reverse direction, that means in the backward direction. So because of all these things, the rate of the enzyme reaction, enzyme catalyzed reaction, will get diminished as the reaction proceeds. But when the concentration is increased, the initial rate of the enzyme catalyzed reaction will increases. That let me show you in a graphical way. So if you consider V as the velocity or the rate of reaction, let me take this as V naught, which indicating initial rate of the reaction or initial velocity of the reaction against concentration of the enzyme. So with increase in the concentration of enzyme, the initial velocity of the reaction will increases. But if you are checking the overall rate of the reaction, the actual rate of the reaction as the time proceeds, then the rate of that enzyme catalyzed reaction will decreases when time proceeds, as the reaction proceeds. But if you increase, say for example, if the concentration of the enzyme is 1 mole per dm cube, if the concentration of enzyme is 1 mole per dm cube, then the corresponding V naught, let me say around 1.3 into 10 to the power of minus 3. Okay, and if the enzyme concentration is 2 mole per dm cube, then V naught will be 1.6 into 10 to the power of minus 3. Initial velocity is increasing. So at say time is equals to, say at time is equals to 1 second. And here also time is equals to 1 second. But when you measure the rate of the same reaction as the time proceeds during the course of time, say if I measure the rate of this particular reaction when the concentration of enzyme is 1 mole per dm cube, but t is equals to 1 second, the initial velocity is 1.3 into 10 power minus 3. But when you measure the same at 5 seconds, then the rate will be 0.9 into 10 power minus 3. Okay, so 0.9 into 10 power minus 3. That means the rate of the reaction got decreased. But when you increase the initial concentration of the enzyme, that increasing the initial velocity, when you are increasing the concentration of the enzyme, the initial velocity of the enzyme catalyzed reaction will increases. But as the reaction proceeds, the rate of the reaction will get decreases. The fourth factor that influences the rate of enzyme catalyzed reaction is substrate concentration. By keeping the conditions pH, temperature and enzyme concentration constant, if you increase the concentration of substrate, with increase in the concentration of substrate, the enzyme activity also increases. But after reaching a maximum, further increase in the concentration of substrate will not increase the rate of a reaction. That means the rate of reaction will reaches to a constant. There will be no further change in the rate of reaction or velocity of the enzyme catalyzed reaction. The reason for this particular phenomenon under the effect of substrate concentration on the rate of enzyme catalyzed reaction is, as you increase the concentration of substrate, the substrate molecule will combine with the enzyme molecule, means the substrate molecule will occupy at their active sites of the enzyme, and the occupation of the substrate molecule at the active sites of the enzyme will continue once all the active sites of the available enzyme is completely filled with the substrate molecule. Then that stage will be the maximum velocity. At that particular stage, the enzyme activity will be maximum because the all active sites of enzyme molecules are occupied with the substrate molecule, so that all the enzyme molecules will be working at a time, so that the rate of reaction will be maximum. But once this stage is reached, then whatever the substrate is left is used only to fill the active site of the enzyme once the product is liberated. Therefore, even though you are increasing the concentration of the substrate molecule, if there is no available active sites for its accommodation, then there will be no use of increasing the concentration of substrate. Therefore, once all the active sites of the available enzyme is completely filled with the substrate molecule, even though we are increasing the concentration of substrate, since there is no available enzyme, there will be no change in the rate of reaction. That means the rate of the reaction will become constant, and that we can show with a simple graphical presentation by taking concentration of the substrate in x-axis and velocity in y-axis. So with increase in the concentration of substrate, the velocity also increases, but once it reaches a maximum, the further increase in the concentration of substrate won't alter the rate of the reaction, so that this will be the maximum velocity of the reaction. And if you have taken the point exactly for half of the maximum velocity, and this particular, the point of intersection will be given as Km, and here Km is called as, Km is a constant and is called Michaelis Menten constant. That means here you can observe, here we have having a hyperbolic curve. So we got an hyperbolic curve over here, right? So here the constant Km is called Michaelis Menten constant, because in order to understand the effect of substrate concentration on the rate of enzyme catalyzed reaction, two scientists by name Michaelis and Menten. Michaelis and Menten derived an expression just in order to understand the influence of substrate concentration on the velocity of the reaction. And the equation proposed by Michaelis and Menten is the velocity of the reaction will be equals to Vmax, that is the maximum velocity, into the substrate concentration whole divided by Km, a constant, plus substrate concentration. Here small v is velocity at a given concentration of substrate, given substrate concentration. Vmax is maximum velocity. maximum velocity. S is a substrate concentration. Substrate concentration at velocity v, and Km, it is a constant called as Michaelis Menten constant. Michaelis Menten constant. So by analyzing this Michaelis Menten equation, it is very much easier to understand the unique active site region of the enzyme, as well as we can get a valid information regarding how actually the enzyme catalysis will happen and how does the enzyme will influence the rate of a particular chemical reaction based on the substrate concentration. So we said Km is Michaelis Menten constant. Shall see the characteristic features of the Michaelis Menten constant, that is Km. So in order to get the exact meaning of Km, we shall consider the Michaelis Menten equation itself, that is V is equals to V max into concentration of substrate whole divided by Km into plus concentration of substrate. So let us consider the velocity of the substrate, velocity at the substrate concentration S will be exactly equals to half of the maximum velocity. So at this condition, so here V is equals to V max by 2, that's equals to V max into concentration of substrate by Km plus concentration of substrate. V max will get cancelled and the equation will get changed. Km plus substrate concentration will be equals to 2 times of substrate concentration, or else when S comes to this side it will become negative, so Km is equals to S. So the Michaelis Menten constant will be equals to substrate concentration when the velocity of the enzyme catalyzed reaction is exactly half of the maximum possible velocity for that particular enzyme. So by this way we can say the exact meaning of the constant, that is Michaelis Menten constant. So the Michaelis Menten constant will be equals to the concentration of substrate when the velocity of the enzyme reaction is exactly half of the maximum velocity which is possible for that particular enzyme. And for each and every enzyme there will be a particular Km value. Thus we can use the Km value, that is Michaelis Menten constant values, in order to characterize the enzymes. And for most of the enzymes, the value of Michaelis Menten constant, that is Km, will be ranging between 10 to the power of minus 1 to 10 to the power of minus 6. This is the range of the Michaelis Menten constant for most of the enzyme molecules. And the value of Michaelis Menten constant will be influenced by the factors temperature as well the ionic strength of the solution. These are the two factors that influences the value of Michaelis Menten constant. Thus here we said the Michaelis Menten constant will be equals to the concentration of substrate when the velocity of the enzyme reaction is exactly half of the maximum velocity. That means when the velocity reaches to maximum, we used to say all the active sites of the available enzyme have been occupied by the substrate molecule. But here we said Km will be equals to the substrate concentration when velocity of the enzyme reaction is exactly half of the maximum possible velocity. That means the Km value will gives information about that at that particular concentration of substrate, exactly half of the active sites of available enzyme have been occupied by the substrate molecule. Therefore, we can easily say the value of Km, that is Michaelis Menten constant, will be equals to the dissociation strength of the enzyme substrate complex formed by the combination of enzyme and substrate. And we know that enzyme substrate complex will actually dissociates to give the product. And the Km may have proportionately higher value, or it may have proportionately lower value also. So if the value of Km is higher the value of Km indicates the weak binding between enzyme and substrate. Suppose if Km value is proportionately low, then that indicates the high binding or strong binding. The strong binding between enzyme and substrate. So Km value will give information about the substrate at which the half of the active sites of the enzyme were occupied. And we said the Km will be equals to the substrate concentration when velocity is exactly equals to half of the maximum velocity. And what does this Vmax will indicate? This maximum velocity actually accounts for the occupation of the substrate molecule completely on the substrate molecule. That means the maximum product formation will occur. That means the maximum velocity will gives information about turnover number of the enzyme. So complete information regarding turnover number of the enzyme can be obtained on the basis of Vmax, that is maximum possible velocity that an enzyme can show at a particular on the basis of enzyme concentration. Now we shall see how to evaluate the value of Km, that is Michaelis Menten constant, and the maximum velocity. And in order to evaluate the value of Km and V maximum, we have to consider the same Michaelis Menten equation. So according to the Michaelis Menten equation, V is equals to Vmax into concentration of substrate by Km, that is Michaelis Menten constant, into the substrate concentration S. So let us take the inversion of this. Shall do the inverse of this particular Michaelis Menten equation. Once you inversed, so it will be 1 by V is equals to Km plus S whole divided by V max into S. Or else we can write the equation as 1 by V is equals to, shall split Km by V max into 1 by S plus, let me write directly, 1 by Vmax. So S and S will get cancelled, so we remain with only 1 by Vmax. So here you can observe the equation what we got over here will resembles y is equals to mx plus c. So it's almost resembling this equation, y is equals to mx plus c. So we know that it's a straight line equation. So when you plot a graph between the term 1 by v against 1 by s, when you plot the graph between 1 by v and 1 by s, that means between the variables y and x, we will get a straight line graph. And now we shall see how that graphical presentation will appear when you plot a graph between 1 by v and 1 by s. So we'll be getting a curve like this. This is the curve we used to get. And when you plot this graph between 1 by S against 1 by V. So here we'll be having an intercept which is exactly equals to Km, sorry, the intercept is equals to 1 by Vmax, that is C intercept. And when you take the slope of this particular curve, you will be getting Km by Vmax. This will be the slope value. So from the slope and by knowing the value of the Vmax, it is possible to get the value of Km, that is Michaelis Menten constant. And when you extrapolate this curve to the x-axis, so whatever the point it will meet at minus x-axis, this will give the value of minus 1 by Km. So this is for this is the curve what you will get when you plot a graph between 1 by S versus 1 by V. And the curve what we have got over here, it is actually called as Lineweaver Burk plot. This is called Lineweaver Burk plot. The straight line graph what we have obtained by plotting 1 by V against 1 by S. This curve is called as Lineweaver Burk plot. This Lineweaver Burk plot, which actually it is useful in evaluating the inhibitors. So inhibitors in the sense, we said the coenzyme and cofactor which is present along with the enzyme protein will increase the catalytic activity of the enzyme. The inhibitor will decrease the catalytic activity of the enzyme. This Lineweaver Burk plot is very much useful in evaluating the inhibitor. That means the nature of the inhibitor will be decided based on this Lineweaver Burk plot by considering this one, the curve what we got for normal conditions. By keeping this as standard, we can measure the nature of the inhibitors. So for example, if the inhibitor is a competitive inhibitor, for that competitive inhibitor, the curve will be obtained like this. So this is for normal condition and this is for competitive inhibitor. For a competitive inhibitor, we will be getting like this, and you can observe the curve is almost passing at the same point of the normal point, but it is the intersection of this particular curve at the negative x-axis is much more closer to the origin, that is to 0. Therefore, we can say, okay, by doing the comparison, we can say that in case of a competitive inhibitor, the slope will increase. The slope will be more and the intercept will remains the same. You can observe the intercept remains the same, but there will be increase in the slope value, and the negative intersect, that is the minus 1 by Km value, will be closer to the 0. But based on this, we can say that there will be no change in the maximum velocity in case of competitive inhibitor, but since slope value will increases, so the value of the Michaelis Menten constant also increases when the inhibitor present in the system is an competitive inhibitor. And let us consider for a non-competitive inhibitor. For a non-competitive inhibitor, the curve will be like this. This is for non-competitive inhibitor. So here you can observe, in case of non-competitive inhibitor, the slope will remains the same. Slope will remains the same, but the maximum velocity have been increased. This is in case of non-competitive inhibitor. So since slope value won't change, therefore the Km value will remains the same in case of non-competitive inhibitor, but the intercept have been changed, so the maximum velocity for that particular enzyme will get changed in case of non-competitive inhibitor, and the value of minus 1 by Km will remain the same as that of normal in case of non-competitive inhibitor. So just by observing, by plotting a graph of 1 by V versus 1 by S for a particular enzyme consisting of either a competitive inhibitor or non-competitive inhibitor, and by doing comparison with the Lineweaver Burk plot for a normal enzyme, we can say whether the inhibitor present in that particular enzyme is a competitive inhibitor or non-competitive inhibitor. Regarding the competitive and non-competitive inhibitors, we shall do discussion in the next video. And that's the whole and sole thing about the effects of temperature, pH, enzyme concentration and substrate concentration on the rate of enzyme catalyzed reaction. So if you like my video, please like it, share it, and do subscribe to my channel and press the bell icon so that you will get the notification for any update in my channel. Thank you.